Hello, everyone. Good evening. So today what I'm going to talk about is failures, my personal failures, our system failures, essentially everything that is not a happy path. Because for some reason, we keep talking about happy paths. So we describe user scenarios, we describe test cases, everything along the fact what's going to happen if everything is absolutely in line, if there's this ideal constellation where every single planet is in the right place, every single system is set up, every single timeout is set up, every single DNS, network, entry, whatever, everything is perfectly 100% okay. And in that case, we know that the system's going to work. So yeah, great. However, the reality is not really that great. And if you ever run some automated tests, you probably know this situation where you run your tests once and okay, this message broker failed, so we have to restart. You run them the second time and, oh, I forgot to turn on this service and I have to do it again. The test failed for the third time, this like end-to-end test of your whole system. And yeah, we have no idea why they failed. We're just going to retry. By the way, retrying is actually a pretty decent scenario, but we'll get into that in a second. So what I want to focus today is everything that can happen badly, everything that can fail, everything that can screw up inside our applications, because happy paths are simple, but handling failures, especially the complex ones, isn't really that easy. But we'll start from the simple things. I really like this quote by, who is it, Gerald Weinberg, that if builders build houses the way programmers build software, the single woodpecker would destroy the whole civilization. And it sounds funny until you realize how you, or I, or any one of you probably, built the last application within the last few years. Like there was this single tiny detail, this single tiny dependency that could literally break everything. Like we don't have access to this, like actually not really that important API. Whatever, the whole web page doesn't load. This single file system ran out of disk space, and we don't even need that disk space for anything because it's just for logging, whatever. The batch process that it was supposed to take like hours, it now fails, and you have to retry it once again because of this one single detail. I see you're taking the photos, probably not of me, but of the slides. If you're taking photos of me, then yeah, here I am. If you're taking photos of the slides, there will be a link to the slides at the very end, so no worries. Anyway, let's move on. Maybe you know this song. There was this really lousy Polish cover as well. The 1 in a million situation is this type of occasion which like rarely or almost never happens. It's kind of poetic. It's 1 in a million. You're 1 in a million, says this guy about a girl. And turns out that in our world, 1 in a million, if you're handling 1,000 requests per second, happens like every 15 minutes. So essentially all the time. If 1 in a million YouTube videos fails to play, it happens every 10 seconds because they play like million videos every second. Every 10 seconds. Let's think about something different. So P99, if you know what it means, P99, it's the 99th percentile. Essentially, it means that the system responds, the response time of the system in 99% of the cases is below this threshold. So if P99 is like, let's say 500 milliseconds, it means that 99% of the users will not see response time above this threshold. Well, at least superficially, if you open up facebook.com, it makes 350 requests just to load the wall, the main page. Probably like 2/3 of it are ads, but anyways, 350 requests. From the basic math, it means that every user experiences P99 latency or above, because there are just hundreds of different requests and they are all unrelated to each other. So let's move on and let's go through some patterns, some ways of making your software more resilient to failures, self-healing. And we'll start from the basics. And when I'm talking basics, I really mean the basics. This is the simplest resiliency pattern you will ever come across. Just catch the errors and, well, not forget about them, but we'll talk about it in a second. So, like, remember that errors happen. Do not just assume that magically everything's going to work and there's never going to be any exception. In languages like Java, where you have checked exceptions, sometimes in some APIs, you'll realize that exceptions can pop up in like the most unexpected places. And you have to learn how to deal with them. If you're programming with Go, you're just like keep typing if error is not equal nil or whatever, so you kind of get more used to it. But anyways, errors are everywhere. So let's think about this really lousily written code. It's a really poorly written code because all of this happens in a single transaction. I don't work in the financial sector, but anyways, let's just go through this. So let's say I'm repaying a loan. And when I'm repaying a loan, I need to send a bank transfer, or I have a single transaction that makes a bank transfer. Then I go to like updating some daily report, generating a PDF, sending that report to a manager that something has changed in the daily whatever. And then I'm waiting for SMTP server confirmation, and boom, I get an exception at the very end. So in a poorly written software, or in a software that assumes that we have this ideal constellation of all the dependencies always working, always on time, everything is properly configured, that's never going to happen. So we don't have to deal with it. However, like every single step you see here, especially this like least important one, can fail. And in a poorly written software, this will roll back the whole transaction. And from the client's perspective, he or she cannot repay a loan with some mysterious HTTP 500, please try again later, because we failed to configure DNS in like whatever. No one really cares. So just put try catch there. Try to do something, maybe put it into a different component or whatever. We'll see, we'll get into a few patterns in a second. The first one, and I'm actually quite ashamed to even call it a pattern, a fallback essentially means screw up this exception and return something different. So this is often explained with a streaming service or a marketplace like Amazon, where you are supposed to display very highly customized recommendations to a user. So like, I don't know, last week you bought a toilet seat, so I'm pretty sure you're going to buy toilet seats till the end of your life. So I'm going to be recommending you toilet seats like till your last day, until you make your last breath. But this is kind of a recommendation engine. But if the recommendation engine for some reason fails, just return like global recommendations, like I don't know, whatever we want to sell right now. If you're in a streaming service and you cannot really recommend the next TV series, just recommend whatever we have in store and whatever you think that's going to be best for like average audience. This doesn't always work. If you're repaying a loan and you cannot make a bank transfer, there is no fallback for that. I mean, you're not going to print some cash and put it in the envelope. But in some cases, think really deeply what you can do so that your whole transaction doesn't fail, but you do have something else in store. It's going to be not as perfect, but we don't need perfect software. We need software that actually works. All right, and speaking of fallbacks and speaking of catching exceptions, you will not believe how important are retries. I mean, this is kind of a joke that like lasts for ages, and every IT specialist will tell you, but this actually works. There are whole frameworks built on top of this idea. For example, Akka or Erlang and Elixir. If your actor fails, we restart it, right? It failed because there was an error, there was an inconsistent state, and you wouldn't believe how many errors are actually transient. And by transient, I mean they will go away if you try one more time. There was a DNS misconfiguration, a service restarted, so we had to wait a little bit. You are calling a dependency that has a garbage collection running and you timed out. All of these situations are actually fairly easy to manage if you simply retry. Just try again. And don't make your users do it, because what users typically do, they will just press refresh, and they will do retry for you. But you don't want your users to do a retry. You want to do it yourself so that no one's even gonna notice. This is a common theme across SREs, that when you're actually, please come in. Oh, no, thanks you. No, never. So this is actually a common theme across SREs. Like, even if our server goes down, our data center goes down, or our region, whatever, yeah, the system just keeps going. No one ever notices it. Maybe it's going to be slightly slower. Maybe this tiny widget is not displayed in our user interface. Whatever. Right? Okay, but when talking about retrying, you should also remember about one thing, and this is actually slightly more complex. So simply retrying immediately will be a big headache, and most likely you will cause a distributed denial of service attack on yourself, because you used to have a dependency which you were calling with some frequency, and now because you are retrying, let's say you're retrying an exception like 10 times, you're now generating 10 times as much traffic. So guess what? You are DDoSing another service. This service will go down, or it will never go up, because you keep bombarding it with requests. More on that in a second. So the idea of exponential backoff is that when making a request, the initial retries should be very fast, because we are sort of heuristically assuming that the problem will go away relatively quickly. However, if it is not the case, because you need a server to restart, or there's like a major outage or something, just keep retrying, but with longer and longer and longer periods of time. And this will actually give that other service some breathing room. Because if you just keep hammering that service with requests, there's no way you're going to survive that. And one more thing, this is actually pretty simple. There's not much difference between a service that responds in 10 minutes and a service that doesn't respond at all, or gives you an error. I was running this ping recently. Tell me you're working from a hotel without telling me you're working from a hotel. It's 12 minutes. I was waiting 12 minutes for a ping from google.com to come back. From my perspective, the internet is down, even though it technically works. It's just extremely slow. So the rule of thumb is that, the first one, the rule 0 is that you should have timeouts on sockets, on network connections, REST requests, database connections, and so on and so forth, as many as possible. But the rule of thumb is that they should be fairly aggressive, because it's a better idea to have a low threshold and then do a retry, because you might, I don't know, reach a different instance that's actually faster, than to have a very high threshold, high timeout, and just wait indefinitely, because you have no idea how fast the system will actually respond. All right, I'm really not into sailing, but I found this picture yesterday on Wikipedia. This is called, these vertical walls that you see here are called bulkheads inside a vessel, inside the ship's hull. So the idea of a bulkhead, it has multiple purposes, but the basic idea of it is that when the water enters the ship, it only enters a single compartment, so a single kind of room inside a ship. So this makes the ship maybe not unsinkable, because we don't have ships like that, but it's much easier to handle smaller leaks. And the same idea applies to writing or developing and architecting software systems. So when you have a large application, monolithic application, and by the way, this is not a sin, it's fine to have a monolith. But if you have a large application which connects to multiple services, having bulkheads essentially means that if one of your dependencies is misbehaving, for example, has a much larger response times, or there's something other broken with it, try to develop the system in such a way that this one dependency doesn't affect calling others, or doesn't affect other use cases. To speak more concretely, let's have a separate thread pool, or a separate pool of memory, or a bunch of semaphores or counters, whatever, for each dependency, so that when one dependency goes down, the rest of the application, even though in kind of a limited scope, it still works. So bulkheading, for example, in my area, so in Java, is essentially means having multiple thread pools for each dependency, rather than one giant for everything. Because if you have one single thread pool, it's very easy to starve all the other dependencies if they all consume the same resources. So one more engineering thing. You don't really see much from the picture, but that doesn't really matter. So throttling is the idea that when you're performing some operations, you should, in some cases, limit yourself. And I will give you a funny story. Well, it's funny now. It wasn't that funny when it happened. I will give you a funny story why throttling is important later on. All right, so you probably know this device. It's a circuit breaker, so it prevents your house from burning down, basically. In terms of software systems, the circuit breaker is a pattern, and there are libraries which implement it. A circuit breaker is a pattern where if you call a dependency, so if you make requests to some APIs or database or whatever, and these requests continuously fail, so you just keep getting errors and errors and errors, or timeouts or whatever, then apparently there is no point in just keep calling that service, because you will just keep getting the same errors over and over and over again. So what you should do? Well, you should get a temporary divorce. You should just cut off that dependency, I don't know, for a minute or maybe a few seconds, let that dependency heal itself. So maybe it needs a restart, maybe it needs some manual intervention, whatever. The circuit breaker, once it realizes that there are a lot of errors happening on the communication side, it just cuts off that dependency. And the cool part, I'm not really an electrical engineer, but the cool part with the computer circuit breakers, the one we use in our programs, is that they can close themselves automatically if they discover that the dependency healed itself. So after a while, they make a single request. If that request succeeded, the circuit breaker closes once again, and our system also heals itself, which is pretty cool. There are many things which can break with a circuit breaker. For example, make sure you understand when it opens, so when it cuts off your dependency. It's perfectly possible that you misconfigure it so that it reacts, it opens when you get HTTP 400 or 404 or 401, whatever. These are your mistakes, not that system. So you should not cut off the system because you are making the mistakes. On the other hand, also make sure that the circuit breaker can actually close. We used to have this situation where the circuit breaker, due to a bug, I don't remember in our code or in it, whatever, when it opened once, we actually had to restart the whole application because it never managed to close itself back. So it was just permanently screwed. And the granularity is the idea of how many circuit breakers you should have. So one per every instance of the calling service, or maybe one for the whole service, or maybe a single circuit breaker. Damn, this was hard. Single circuit breaker for like a whole application. Probably a bad idea, but you have to think about it in advance because this is a really powerful tool. And when talking about timeouts, retries, circuit breakers, there's this phenomena called thundering herd problem. And essentially, this is the idea that multiple systems, multiple instances, multiple nodes are making requests at the exact same time to some dependency. So when the load is spread over time, so when it makes requests like evenly on the time axis, everything is fine. However, when it happens that every single instance or every single system makes a request ideally at the same time point, you're going to get into troubles. You're going to get into troubles to the point where that system is hammered with so much traffic that it essentially immediately goes down. So what happens? Every single system that was making these requests schedules a retry, let's say after 1 second. So then there's silence for 1 second. And after 1 second, you get another spike of traffic. So the database goes down or whatever you were calling. So this is why it's called thundering herd problem. It's fairly easy to fix. For example, when you're doing retry, your retries should be randomized. So don't make a retry after 1, 2, 4, 8, 16 seconds. Add a little bit of jitter to it so that the load is spread evenly. And a similar problem, cache Stampede. I remembered about this because of this funny headline. It was like 10 years ago. Cache Stampede is essentially a situation where the cache is cold initially, and the system receives so much traffic when it starts up that the cache never manages to warm up. So until it warms up, the system received so much traffic that it actually went down once again. And we go back to point 1. The system starts up, the cache is cold, and we receive so much traffic that we never really manage to go back to normal state. Also, there are some patterns to fix it, but we'll get into that in a second. All right, this was all simple, so let's move into more kind of complex domain, so everything that's asynchronous. The good news is that if you do some stuff asynchronously, chances are you will never notice there was an error because the error happened like in some other system, in some other thread, so yeah, whatever. I don't really care. And the same happens if you use, I don't know, futures, promises, async await to a certain extent, streams, actors, whatever. If you offload work to some asynchronous entity, actor, thread, process, node, whatever, if you don't check for the result, you will never notice that there was an error. It's a /feature. Of course, I'm kind of joking a little bit here because you should check for the response, but at least your current transaction will not fail. So if you remember this previous example of repaying a loan, the situation was that we had a really, really long transaction, and at the very end, very tiny detail failed. It was sending an email or something like that. If you offload sending an email to a different service and do it asynchronously, even if it fails, I don't really care. All right, so the same happens, by the way, with thread pools, coroutines, goroutines, virtual threads, actors, agents, whatever. The same situation. So you offload some work and you don't have to deal with exceptions. At least you don't have to deal with them now. And it's much easier to think about errors if they actually happen asynchronously in some different domain. And this brings us to like everything that's related to message queues or message buses. So every time you want to make sure that you have like a core transaction and then you have a transaction that's actually doing some less important work, or maybe this less important work is actually important, but it takes a fair amount of time, just put it in a message queue and let other system do it. This could actually spread into like multiple hours of talk. So like, let's stop right here. But the general idea is that it's fairly easy to split complex long-running workload into multiple stages once you have some notion of a message queue. However, the new solutions bring us new problems. So what happens, for example, and this is just one of the things, what happens if the receiver fails to consume a message? And it can happen for multiple reasons. The consumer failed in the middle. The consumer timed out because it was processing the message for so long. There was an exception or any kind of error when consuming a message from a queue. What happens then? I mean, I won't give you an answer, but you should know if you're using any message broker. Is it RabbitMQ? Is it some proprietary message broker? Is it PubSub from Google? Whatever. What happens then? Are there any retries? So will your message go back to you? Will it go back to another instance that's maybe healthy? Maybe, I don't know, maybe there are some timeouts. So how much time can you actually spend receiving a message? Because at some point the broker will just assume that you're dead. So think about it. DLQ, dead letter queue. What happens with messages that are like dead on arrival? So not really dead on arrival, but like there were retries, there were timeouts, and the message broker has nothing to do with the message. Does it just poof, disappear, or does it go to a different queue? Where is that queue? What do you do with it? Maybe you forgot that there is a DLQ, and after 10 years in production, it has like millions of messages. Happened to me once. There's also head of line blocking. So if you fail to process a single message, what happens with all the subsequent messages? Are they stuck in a queue? Are there any other nodes that can process subsequent messages? What happens with the order of the messages? You should be prepared for that. You should understand the semantics of your message broker. At least once delivery, something that we could probably talk for hours as well. Just understand what are the guarantees. So if you put a message in that message queue, do you have a guarantee that it will ever arrive at the destination? And how can idempotency be implemented? So idempotency is another term when it comes to at least once delivery. Essentially, I mean, there are many definitions, but essentially it means, can you retry? So is retrying safe? There are operations that are inherently unsafe to retry. When you're charging someone's account, you cannot just retry it because most likely you will charge the person twice. But it can be fairly easily fixed, but you just have to understand it and you have to understand the consequences. I just noticed, and it seems like a week ago it became deprecated, but there's nothing preventing us from using it anyway. So there's this HTTP header, which is semi-standard, called idempotency key, which essentially means when I'm making this HTTP request, if I retry that request with the same key, it should be ignored. So if the receiving party, the server, notices that the same request was already made, you can safely ignore it. All right, the Outbox pattern, I'm just like pushing patterns to you so that you can follow along later on. The Outbox pattern is it's a fairly simple pattern which allows you to transactionally send messages to another service. And within a single transaction, I'm like using air quotes here, within the single transaction, you can actually make some change to a database and send a message. It involves kind of a special table. It involves a separate kind of thread or process that processes these messages, but you kind of get the idea. All right, and let's move even further. So let's move into more complex scenarios. So when doing a multi-node deployment, so when you have multiple nodes, it's very often the case that you have to perform a certain action only on a single node. You don't care which one is it, but you don't want to duplicate work. So you have some background job or whatever. You can use leader election, understand how it works on your infrastructure. So we can implement leader election on like in hundreds of different ways. Some of them are better, some of them are worse. From the theoretical point of view, you are basically doomed because there's no way to do it kind of like very, very reliably. But you can have something that's fairly fine. This one node here, leader is not a singleton worker. What I mean by that is that when a node becomes a leader, it doesn't necessarily mean that the leader has to do all the work. It just means this is the one that has the voice. So the leader can just dispatch work to other nodes. All right, and this is actually not very cloud native. So if you're building into the cloud, this will not work really well, but it will work well under some classes of problems. So the local database, or the concept of local databases or offline first applications, is the idea that rather than using a database that is somewhere, and if it's somewhere, then it's of course prone to all sorts of errors, use a database that's stored locally, for example, on your local disk. And then you perform some sort of offline replication, or sorry, asynchronous replication somewhere in the background. And in that case, chances are that your application will survive some external database crashes, even if your users keep using it. So the whole kind of movement is called offline first. And that's the basic idea, that you keep your data locally. As I said, this is completely like the opposite to what you've heard when it comes to cloud native development. But maybe that's something you can actually use at your particular project. So you have an application that's actually working offline very well. It can even be a browser application, but its primarily data storage is local. And then it's just periodically synchronizes data with some server or maybe with some other nodes. I mean, it sounds crazy once you realize this is essentially Git. So this is how Git works. Until we all started using GitHub, which is just this one central repository, and no one can work without it. All right, moving on. When talking about applications working offline, or when talking about applications that can survive crashes that happen somewhere, you can also investigate a pattern called, I don't know, maybe I made up this term myself, but whatever. A failure backlog essentially means that if there was a failure, so if you didn't manage to make a request to some external service, that's fine, but don't simply log it, but put it into some persistent queue, into some local storage, so that you can try to retry later, maybe even hours later. Maybe you have an application that has internet connection like just every few minutes or every few hours. So have a backlog of operations that are safe to retry later on. And talking about cache stampede, one more pattern when deploying applications. The gradual startup essentially means that your application can handle traffic gradually. So it doesn't take all the traffic immediately once it's ready. It starts with 1%, 2%, and so on and so forth. This way, it has a little bit of breathing room to warm up its caches. So you don't get into a situation where your application crashes immediately once it starts serving traffic. So it works fine if no one calls it, but once it starts to receive the traffic, you are essentially doomed. One more thing, and this is like more or less Kubernetes thing, but a useful one. Distinguish between two states. Your application is up, so it started and it can serve traffic, and your application is up and running, so it not only can serve traffic, but all the dependencies are warmed up, and the application is initialized. So for example, it loaded some static dictionaries, it loaded some cached data, and so on and so forth. So it warmed up itself. All right, and I think the last part, and this is something I cannot really emphasize enough, if it's possible in your application, try to have a mode called Dryrun. So let's imagine you are going to, I don't know, taking a loan, a mortgage or whatever, and you ask how much is it going to cost? So what's going to be the monthly payment? And the person in the bank says, I don't know, you have to take the loan first and then you will know. But it doesn't happen, right? They are fully capable of simulating what is gonna happen. They know they can see like what is gonna be your payment plan. And the idea of a dry run is somewhat similar. So rather than performing a complex and probably very heavy transaction, allow users to see what's gonna happen in if you run that transaction. So this doesn't just happen like overnight. You have to design your application in such a way, but this is extremely useful. And if you're into DevOps kind of things, Terraform Plan does exactly that. So without making changes to the infrastructure, it shows you, okay, if you run this command in a non-dry mode, I am gonna perform the following changes to your infrastructure. This is extremely useful because you don't wanna make changes without knowing what's it gonna be. A similar pattern is a compensating transaction. So let's say you don't have a dry run, you perform a transaction which failed for some reason. And sorry, I don't mean fail. It succeeded, but it succeeded in some unpredictable way, and now you want to roll it back, but not roll it back in a database sense. You want to like put the system back in the normal state. This is the idea of compensating transactions. So essentially, you want to have a possibility to revert the changes with full auditability, with full knowledge of what happened on your system. The easiest example, let's say you made a mistake when, I don't know, sending a bank transfer or whatever. Compensating transaction is just getting your money back. So the mistaken transaction doesn't disappear. It's just covered by a compensating transaction. And when talking about compensating transaction, one level above that is a so-called Saga. And this is the pattern where you split very complex distributed transaction, or sorry, I shouldn't say distributed transaction, a distributed process which spreads across multiple transactions. You split it into multiple steps, and Saga keeps track of which point of this process you are at this moment. So when something fails, like in half of the process, you can always run a sequence of compensating transaction, essentially rolling back all the steps. All right, so talking about throttling, let me tell you a story we I want to say I experienced. We actually did it. So we once sent 700,000 messages, text messages to a single person. I was reading this CRM when the customer was contacting this telecom, and this really escalated quickly. It was from something like the customer is concerned, the customer is pretty upset, the customer is swearing, and yeah, so there were like a ton of things that we did poorly. There were systems communicating via database. So one system puts something in the database, another one reads that database. There were transactions with no isolations. There was a database used as a queue. Tons of things, but that doesn't really matter. I mean, we screw up, okay? But the problem is that we designed a system that allowed sending 700,000 text messages to a single person. There's no way in hell the system would ever be required to do so. I mean, I cannot imagine a use case that requires sending 700,000 messages to a single person ever. But we didn't have any measures to circumvent that. I mean, essentially, the system was just doing what it was supposed to do, but we never really thought about any safety mechanisms. Just like the company called Knight Capital, they didn't have a thing which is fairly common in the financial sector called kill switch. So doesn't really matter what happens, they screw up the deployment, but after the deployment they were losing, they lost like almost $500 million in 45 minutes. In 45 minutes, so just to give that into perspective, it's $1 million every 6 seconds. To give that into perspective, Bill Gates makes barely $8,000 in 6 seconds. So that's the kind of scale. After 45 minutes, they just shut down the production because like the whole stock market was seeing that something bad is happening. And they didn't have a kill switch. They didn't have a mechanism that would quickly figure out that they are making too stupid transactions too fast. It was fairly simple to figure this out. All right, graceful degradation. So that's another thing regarding deployment. So if your application starts to malfunctioning, you can do 3 things. You can ignore it and let your customers know it, or tell it to you. You can shut it down, or you can put your application into kind of semi-working mode. So maybe some features are not working because of circuit breakers, because of timeouts and so on, but the rest of the application still keeps working. So if you're an application like, I don't know, Facebook or Netflix, and there's this tiny little service that misbehaves, you're not just gonna shut down Facebook. You will say that your wall works, your likes are still working, your photos are working, Messenger is not working, right? Or whatever, or vice versa. So the system goes into a less functional, but still functional state. And closing up, my final remark for you is that you should test your resiliency. Not only test your happy paths. Do not build your use cases and your test scenarios around what happens if everything is aligned perfectly and every single detail within your application is aligned ideally. Also, test what happens when less or more crucial parts of your system are broken. So what happens if the database doesn't work? Most likely you don't work as well, but maybe you have to. Maybe someone requires you to do so. What happens if this really not important Facebook ad pixel doesn't respond? Probably you shouldn't even notice, and so on and so forth. What happens when a system that was consuming messages was down for 3 hours? Will it pick it up? Will it pick up the messages, or will it just go down? Test for resiliency. And there are plenty of ways in which you can do it even automatically. For example, there's this thing called, I don't know, Toxi proxy, I believe. So it's a TCP/IP proxy that can inject faults into your network traffic. There's also the whole chaos engineering movement. So it was talked over many times. There's Chaos Monkey and the whole Simian Army family of software. If you don't know what is Chaos Monkey, it's essentially a piece of script, simplifying greatly. It's a piece of script that kills your testing or production instances and making sure that your system as a whole still works. So that's a fairly simple complex and concept, and it can actually reveal a ton of things. And last but not least, so if you have no idea what's going on, if you have no idea what's going to happen if your system fails, if you have no idea in what kind of failure modes it can jump in, and I remember this quote. I'm not going to quote it probably ideally, but it was something like, complex systems fail in unexpected ways, and boring technologies fail in expected ways. And I hope you get the idea. So if you have a boring technology, then like the whole internet knows how to fix this stuff. If you have a really complex technology, very modern technology, or something that was just like tested by these 2 startups somewhere in Hong Kong and Beijing, then most likely no one in the internet knows what are the failure modes. It's going to fail in like ways that are absolutely unexpected. So prefer boring technologies. But that wasn't the point of this slide. It's just something that comes to my mind. But the point of the slide is that if you don't have any testing in place, if you didn't think about failure modes in which your system can come into, at least have some observability in place. It was never as simple as now due to OpenTelemetry and due to multiple APM products like Datadog or New Relic on the market. Here are a few links, but you can check out the links here because we just ran out of time, so you can grab the slides here.